This video is going to cover Chapter 2, Section 5, or the first part of Chapter 2, Section 5, the Fundamental Theorem of Algebra. You want to make sure that you're taking notes while the video is going, and then at the end of the notes, you're going to submit your notes. So we start with linear factorization theorem, which basically just says if f of x is a polynomial of degree n, where n is greater than 0, that means that x has to have an exponent, then f of x has precisely n number of roots. So whatever my f of x is, I'm going to look at the highest exponent, and that's going to be equal to the number of roots. Now, these can be various kinds of zeros or various kinds of roots. They can be rational roots, which are what we're used to, like a fraction or a whole number, positive, negative, 0. Any of that would be rational roots. They can be irrational roots, which would be square roots of non-perfect squares. And remember, those come in pairs. Or they can be imaginary roots, complex imaginary roots involving I. So these come from the real zero side, and these the non-real zeros. So when I say that I have something that is x to the fourth, it doesn't mean that there are 4 real roots. There's just 4 roots or 4 zeros or 4 solutions. And they can be made up of rational roots, irrational roots, imaginary roots. All right, so example 1 just says find the exact number of zeros. Again, you're going to look for the highest exponent. It is 3. So that is the answer. There are 3 zeros. Example 2 says solve the function. So remember, when we solve the function, we replace f of x with 0 and then solve it however we can. Factoring, using the even root property, sometimes using the quadratic formula. You could complete the square if you wanted to and it was quadratic. There's lots of different ways. So we start with just replacing that f of x with 0. And then this is not the difference of 2 squares. It's pretty close, but it's not the difference of 2 squares, so we can't factor it. What we would do is subtract the 36, and I would get negative 36 equals x squared. And then I want to square root both sides of the equation, putting a plus or minus in front of the square root of negative 36. Now, up until the last lesson, we would have said that this is no real numbers, but now we're including imaginary roots as part of our answers. And we know that the square root of negative 36 would be plus and minus 6i. So remember, there are 2 roots. This time they are both imaginary, negative 6i and positive 6i. B says f of x equals x to the third plus 25x. So I know that there are 3 roots. 0 equals x to the third plus 25x. I can factor out an x here. And the left side can be solved, and then the right side can be solved separately, not factored further because, again, it's not the difference of 2 squares. From the left side, I get x equals 0, and from the right side, I'd get x squared equals negative 25. Square root both sides, putting that plus and the minus on the front, and I get x equals plus and minus the square root of negative 25, which is 5i. So my zeros are negative 5i, positive 5i, and 0. There's 1, 2, 3 of them, just like we said from the beginning. Okay, example 3 says find all the zeros of the function and then write the polynomial as a product of linear factors. So we're doing the zeros just like we did. Then we're going to write it as a product of linear factors. So if we look at A, replace f of x with 0. This is a trinomial, so we can't just, take out the x. We would be looking for factors of 1 that sum to negative 3. There are none. So our other options are complete the square or use the quadratic formula. So since we want to practice that one, we're going to do quadratic formula. Negative b plus and minus the square root of b squared minus 4ac all over 2a. The A here is 1, the B is -3, and the C is 1. So I would get negative B, which becomes positive, or sorry, -3, which becomes 3, plus and minus the square root of -3 squared minus 4 times A times C all over 2 times A. 3 plus and minus the square root of 9 minus 4 over 2. And I get 3 plus and minus the square root of 5 over 2. Now those are my zeros, and there are 2 of them to match like I said before. Here's the tricky part. Writing this as a product of linear factors. So, because the leading coefficient here is +3, I would do x minus 3 minus root 5 over 2. And I would do x minus +3 plus root 5 over 2. Now, in order for this to be a linear pair, I've got to do 2 things. One is distribute that minus to both the terms in what follows. So this could also be around parentheses. The second thing is you have to get rid of the 2 in the denominator. So a linear factor can't have a fraction in it. So we get rid of the over 2 by multiplying the x by 2. If I did it over here, it would cancel out. So I end up with 2x, this distributes to both, minus 3 plus root 5, multiply by 2 here and by 2 here, and I get 2x, distribute here, minus 3 minus root 5. So this is the factored form, or the linear factors, of a polynomial with roots that are 3 plus and minus root 5 over 2. So remember, linear, it can't be squared, first of all, and it also can't have that fraction in it. All right, now let's look at B. So B says, again, we're going to replace the f of x with 0. 16x to the 4th minus 81. This time, it's the difference of 2 squares. So I have 2 options: add the 81, divide by 16, and take the 4th root, or factor what's here. So I can get 4x squared plus 9 and 4x squared minus 9. The first parentheses can't get factored any further, but the second one can. 2x plus 3 and 2x minus 3. Now I can set each of these equal to 0, and then also set my 4x squared plus 9 equal to 0. So I'd subtract the 9, divide by 4, x squared would equal -9/4, square root both sides, putting the plus and the minus out front, and I'd get x equals, the negative comes to the outside, this would be the square root of 9 over the square root of 4, so I get 3 over 2i, and the plus and minus stays with it. The second parentheses, 2x would equal -3, and x would equal -3/2. The last parentheses, 2x would equal 3, and x would equal 3/2. So my 4 zeros, and there should be 4 because the exponent's 4, are -3 over 2i, +3 over 2i, -3 over 2, and +3 over 2. Now the linear factors would be x, change the sign, so plus 3 over 2i, x, change the sign, so it's minus 3 over 2i, x plus 3 over 2, and x minus 3 over 2. Because they all have a denominator of 2, I've got to get rid of them. I'm going to multiply each of the x's by 2. So 2x plus 3i, 2x minus 3i, 2x plus 3, and 2x minus 3. Now the good thing about these is with extra time, if I actually multiplied all of these out, and those are 2 conjugates, so you can use the shortcut for the conjugate with the imaginary numbers here, the a squared plus b squared, and for the difference of 2 squares on this one, a squared minus b squared. And then you could FOIL that out and check your question, so it should match your question. All right, example 4 has a multi-step. So it says find all the possible zeros of the function, find the actual roots, write the polynomial as a product of linear factors, use the factorization to determine the x-intercepts of the graph, and then use a graphing utility to verify that the zeros are the only x-intercepts. So we start with possible zeros of the function. So we go back to making sure this is in decreasing degree order, and it is. Factors of the last would be 1 and 16, 2 and 8, 4 and 4. Factors of the first would just be 1 and 1. So my possibles are plus and minus 1 over 1, 2 over 1, 4 over 1, 8 over 1, and 16 over 1. That's the first part. Find the possibles. Then it says find the actuals. So we're going to have to test these out. Let's see if Descartes' rule helps. This is 1 sign change, 2 sign changes, 3 sign changes, and then it stays the same. So there are 3 or 1 positive roots, which means I'm going to try all my positives first. I'm not even going to worry about the negatives just yet. So start with 1 on the outside. 1, negative 4, 8, negative 16, and 16. Bring down the 1. Doesn't work. Go to 2. And 2 works. So now I'm going to take this, add in my x's. And it's not quadratic, but let's see if this is factorable by grouping. So from the first set, I can take out the x squared, and I get x minus 2. Second, I can take out the 4, and I get x minus 2. X minus 2, x squared plus 4 are my remaining factors. They're not linear, but they are the factors. So then to solve these, I would get x equals 2. X squared would equal negative 4. Square root both sides, doing the plus and minus. And x equals plus and minus 2i. So my 4 roots are the 2 I found from the possible roots, so my actual roots. 2, the 2 I found from here, so it's a repeated answer. You don't need it twice, but it is important to identify that they're both there because that's how I know that there's 4 roots. And then negative 2i and positive 2i. It's also important to include both 2's when we do our linear factors. So this would be x minus 2 times x minus 2, x minus a negative 2i, so x plus 2i, and x minus 2i. So we don't group these together and square them because then it's no longer linear. We keep them spread out like that. That's product of linear factors. Now comes use the factorization to determine the x-intercepts of the graph. So think about what you actually see on a graph. Do you see imaginary roots on a graph? The answer there is no. So my x-intercept should just be my normal real roots. So the only x-intercept I should actually see is 2, 0. Now we're going to put this into a graphing utility to test that out. So I entered that function into my graphing utility. I hit graph and notice that it only intersects my graph at 1 point, which is at that 2, 0. It also bounces at that 2 point, which matches our multiplicity of 2. So remember that if the 2 roots, it should bounce at that point. All of this stuff should start to overlap. All right, so we talked about conjugate pairs in 2-4 to use conjugate pairs to eliminate the denominator having an I. Now we are just using the conjugate pairs because if one imaginary number is a 0 of a function, then we know the conjugate also has to be a 0 of the function. So if I just told you that 2 plus 7i was a factor of this function or a zero of the function, you automatically know 2 minus 7i is also a factor. Is also a zero of the function. If I just said 17i, then negative 17i would also be one of the zeros of the function. So they always come in pairs. Think about it. You've never seen a f of x with an I in it. So we always do them in pairs so that they would cancel out when we FOIL it out. So example 5 says, find a polynomial function with real coefficient that has the given zeros. So we're going back to 2 when you were given the roots and you had to find the equation, except now we're involving imaginary numbers. So A says 3 is a root and 3 plus I is a root. You have to remember that if there's an imaginary root, its conjugate is also a root. So 3 minus I is also a root. Then we're going to put all of those behind the x. Distribute that negative to everything after the x. So it should change the signs of all the terms that are there. And then we're going to FOIL this out. We're going to multiply it out. Since we know that these are conjugates and they are going to cancel out the i's, do those first. So don't forget about your x minus 3. But then FOIL this first. So x times x is x squared, negative 3x, positive ix. Go to negative 3 times x, negative 3 times negative 3, negative 3 times I. Go to the negative I, positive 3i, and negative I squared. Now what should happen in this step is all of the terms with i's on them should cancel out. And then anything that's got an I squared, you're going to replace. So the x minus 3 is still here. Positive ix and negative ix cancel out. Negative 3i and positive 3i cancel out. And minus I squared would become minus a negative 1, which becomes plus 1. Now combine your like terms. X squared is the only squared. Negative 3x and negative 3x is negative 6x. Positive 9 plus 1 is positive 10. And now I've got to FOIL these out. So x times x squared is x to the third. X times negative 6x is negative 6x squared. X times 10, 10x. Negative 3 times x squared. Negative 3 times negative 6x, and negative 3 times positive 10. Combine your like terms. And set it equal to f of x. So f of x equals x to the third minus 9x squared plus 28x minus 30. Okay, we're going to do it one more time, and then we're going to stop here for today. So looking at B, if 5 minus 3i is a root, so is 5 plus 3i. I would do x minus a negative 2, so it becomes x plus 2. X minus 5 plus 3i. Remember, the negative changes both signs. X minus 5 minus 3i. Multiply out the second two polynomials first. So I'm going to get x plus 2, x times x times negative 5, x times negative 3i. Then negative 5 times x, negative 5 times negative 5, Negative 5 times negative 3i. Then 3i times x. Then 3i times negative 5. Then 3i times negative 3i, negative 9i squared. Check to make sure all the terms with the i's cancel out. So negative 3ix and positive 3ix. Positive 15i and negative 15i. And then the negative, or the I squared becomes negative 1, and this becomes a positive 9. So I bring down the x plus 2, and then I get x squared is the only squared. Negative 5x and negative 5x is negative 10x. Positive 25 plus 9 is positive 34. And we distribute this one last time. X times x squared, x to the third. X times negative 10, negative 10x squared. X times 34, positive 34x. 2 times x squared. 2 times negative 10. And 2 times 34. Combine your like terms. X to the third. Negative 10x squared and positive 2x squared is negative 8x squared. Positive 34 and negative 20 is positive 14x. And then the 68 is the constant by itself. Set it equal to f of x. And there's the function that would result in the original given zeros. All right, so we're going to take a break here for today. You're going to make sure you submit your notes to the assignment now. Do so before the end of the class period. And then use the remaining time to start the 2-5 homework. Don't forget that you also have your quiz video that you can work on over the weekend. It's due Tuesday. Have a great weekend, and I will see you soon.